We propose a new algorithm for performing sequential scene parsing that uses semantic segmentations and model-based pose estimations to generate a temporally and physically consistent scene model. Let S of t be a scene configuration hypothesis. Estimating the best scene model given an input data can be done by finding the scene that maximizes both the probability of the input data given the scene configuration and the consistency between the current configuration and the best prior scene configuration. In addition to the data and temporal consistency, we introduced the physical consistency measure C with an associated probability that penalizes physical consistency violations. We will consider three kinds of constraints in C, which is stabilities, collisions, and support relationships. Let S of C denote a set of physically consistent scenes and S of H denote a set of scene configurations generated from pose estimators. Since pose estimators do not enforce physical constraints, performing scene estimation from S of H directly often does not yield a good result, since the best model generated from that set often violates physical consistency. Instead, we'll first try to improve the input scene configurations by simulating scene hypotheses in a physics engine to eliminate collisions while applying gravity to improve all object stabilities and applying guiding forces to maintain the scene model consistency with the input data. This procedure will generate a new set of hypotheses f of h prime that contains a set of more physically consistent scene configurations which is then used to estimate the best scene model. In order to effectively find the best scene configuration, instead of testing all possible scene model in S of prime, we'll incrementally optimize the scene model from the base of the structure to the top of the structure. This following video demonstrates the full scene parsing algorithm. The scene model with the maximum data correspondence is first simulated to estimate the general structure of the scene. The structure is compared to the previous scene to categorize each object as edit, remove, or support retain object. This mode of change is then used to determine the number of hypotheses from the previous scene is re-evaluated and the number of hypothesis evaluation that needs to be performed in the scene model estimation. To perform the scene optimization, all objects that are connected to the ground will firstly be added and optimized. If those objects support other objects, the stability of the supported object will also be considered for selecting the best hypothesis of the supporting object that maximizes the scene probability. This process is continued until the optimum scene configuration is found. This following video shows the sequential scene parsing algorithm used in the block stacking task. In this task, the scene parsing will provide both physically consistent object poses and the current structure of the scene. Based on the detected structure, the robot will grasp the free block and put it on the top of the stack. To speed up the best scene estimation in this test, the scene parsing will only consider the best pose hypothesis from the pose estimator that correspond to the maximum data consistency. Even though the sequential scene parsing algorithm is only performed on a very limited number of hypotheses, object poses can still be reliably corrected and the block stacking task is still completed successfully. We believe our sequential scene parsing algorithm have a huge potential for many robotics applications that requires object manipulations. In the future, we plan to support scene model input generated with SLAM-based techniques such as kinect fusion and support more complex object interactions such as magnetic property and grasping, which will potentially improve the accuracy of the scene approximation and the applicability of our algorithm.